So our next presentation is by Jennifer Tully, who's with the US EPA Office of Research and Development in Cincinnati. I know a lot of the staff there. One of their staff used to work here, and so I've been pretty close with some of those folks. And I know Jennifer works with my colleague Mike Schock a lot. And so I haven't met you, Jennifer, but I'm looking forward to maybe doing that this fall at the Small Systems Workshop when you guys host that. But today, Jennifer is going to talk about understanding lead and copper corrosion issues and sampling strategies with private water systems.
Good morning. So my talk today is on understanding lead and copper corrosion issues and sampling strategies with private water systems. It's put together by myself and my co-author Mike Schock. We're both with the US EPA Office of Research and Development in Cincinnati, Ohio. I'm a physical scientist with the US EPA, and for the past 5 years I've been working on examining the scales that build up on the inside of lead service lines and also looking at various sampling protocols and strategies for looking at the occurrence of lead in drinking water. So going through the outline of the talk this morning, so we're going to be looking for the potential sources of lead and copper in a premise plumbing and a private water system, looking at the water quality parameters that can affect metal release, and how to go about sampling for lead and copper. And we're not going to focus on regulatory sampling. Instead, we're going to focus on different sampling strategies that can help to identify sources of lead and copper in the premise plumbing system, and also how to go about estimating exposure, so figuring out whether or not somebody is exposed to certain amounts of lead or copper in their drinking water. So to start off with, we'll look at the Ban on Lead in Plenuming. And this is the Reduction of Lead in Drinking Water Act, which prohibited the use of any pipe or plumbing fixture, fitting, any solder or flux after June of 1986 that was going to be installed in a residential plumbing system, so water that's meant for human consumption, that is not lead-free. And on the surface, that looks pretty good, right? We want to have lead-free plumbing components in our drinking water systems. However, the definition of lead-free has changed over time. So back in 1986, it was defined as solder and flux with no more than 0.2% lead and pipes with no more than 8% lead. In 2011, that definition was refined down to the weighted average lead content of 0.25% across the wetted surfaces of plumbing products, but there was no requirement that manufacturers or suppliers certify that their products met that standard. And in 2020, the definition remained the same, but a requirement was added that manufacturers and importers had to certify that their products met this new requirement through third-party verification. And this third-party verification is shown through the NSF ANSI 372, which tests for total lead content in plumbing components. And then as an additional step on that, there's NSF ANSI CAN 61, which is Drinking Water System Components Health Effects, and that incorporates this lead-free requirement with the Reduction of Lead in Drinking Water Act, but also adds a more stringent leaching requirement. So it tests various plumbing components in different test waters and sees how much lead and other contaminants of interest leach out of the plumbing components, because the total amount of lead present in a plumbing component isn't necessarily indicative of how much lead is going to come off when it's installed in a residential plumbing system. Now, a bit of an issue with this and private well systems is that there's no regulation or national regulation on the types of plumbing materials that can be installed in private water systems. So that seems to be on a state-by-state basis on whether or not there are regulations and requirements as to what can be installed in a private well system. There are seemingly local trade groups that kind of have standards where they promote the use of lead-free products in private well systems, but there's not a set national standard for not using potentially leaded products in private water systems. So looking at the various sources of lead in drinking water, this is a little schematic from the US EPA, and we'll look at some of these various sources in the field. So I have a couple slides of images of what these types of sources look like out in various residences and out in the ground. So we have copper pipe with lead solder, so solder that was made or installed before the 1986 Reduction of Lead in Drinking Water Act ban. We have lead service lines. These are pure lead pipes that connect the water source to the residence. We have faucets, so the various fixtures and fittings inside the home can contain lead within those metal components. Galvanized pipes, so these kind of have a twofold way that a lead can be introduced into the drinking water, and I'll talk about that a little bit more in the subsequent slides. And then lead goosenecks, these are just shorter segments of pure lead pipe that were used to connect two rigid pipe materials because lead is very flexible and you can easily connect them together when necessary. So looking at some of these out in the field, here we have a full lead service line. We have partial lead service line replacements where a portion of the lead service line is replaced with copper. There's an example of the lead gooseneck, so you can see kind of how that got its name. And then the lead line galvanized iron is a bit of a Trojan horse because on the outside, if you were looking at somebody's plumbing in their home, it would look like a galvanized pipe, but in reality, it's lined in lead. And you would only know that it's lined in lead by either sampling the drinking water and finding higher concentrations, or actually taking the pipe out of service and cutting it open, and then you would see that lead lining. So it's going to behave like a lead pipe, even though from the outside it looks like a galvanized iron pipe. And these pipes we've identified along the East Coast and also a little bit in the Midwest, but we're not really sure how prolifically they were used across the United States. Some other sources of lead to drinking water, lead tin solder, various brass fittings and components, so shutoff valves, brass water meters, the faucet components, again, the various metal pieces that can be inside of faucets can potentially contain lead. And if we move over here to galvanized pipes, so this is one that I mentioned earlier. So these pipes intrinsically contain zinc and iron, but they can also be a source of lead, cadmium, and copper. So this is those are also some elements that can be found in the coating on these pipes. And because of that, they are a source of lead, and they should never be used for well casings, which are going to come into direct contact with drinking water, and they should also not be used for any drinking water plumbing because of the potential to leach lead and cadmium and also copper. And so if it's already in use in somebody's premise plumbing, that is something that would need to be investigated because it is a potential source of lead, not only from that coating, but galvanized pipes that are connected downstream of lead sources can act as a sink for lead. So you have lead coming off of those upstream sources and it's sorbing onto the galvanized iron scale, and then it can be re-released from that galvanized iron scale. So there's kind of a twofold mechanism that galvanized pipe can contribute and prolong lead release to drinking water. If we look at some of the sources for copper in drinking water, some of them are the same as the ones for lead. So we again have the brass valves and fittings, the brass water meters, various faucet components. We also have bronze, so copper is present within the bronze alloy. So you have bronze pressure reducer, valves, various fittings, and then of course copper pipe itself is going to be one of the major sources of copper to drinking water. If we look at a private well system, there are several parts and pieces of the well that can come into contact with drinking water. Some of these are going to be the same as some of the various plumbing components that were identified within the premise plumbing that can contain lead and copper, and some of them are going to be a bit different. So we have, again, the pipes, we have various soldered joints and valves, the well casing, that is one very particular to the wellhead itself, the T's, adapters, the pump, and the pressure tank. So in addition to all the potential sources of lead and copper in the premise plumbing, you have to also take into account all of the various sources of lead and copper between the well and the residence, and also within the well structure itself. So if we move on to the various water quality factors that affect metal release, there are a lot of them. So it's a really good idea to characterize your drinking water and to really know what your water quality, or your background water quality is. So in a private water system, some of the more important water quality factors that are going to affect metal release are the pH, particularly if you have a low pH system, that's going to be more corrosive. The oxidation reduction potential, the alkalinity of the drinking water and its dissolved inorganic carbon, carbonate content, the levels of chloride and sulfate, and also if you happen to have a source water that's high in iron and manganese, these things can aggravate the current scales that are there and potentially act as sinks for metals such as lead and copper that then can be re-released. But all of these water quality factors and probably several more will impact metal release in a drinking water system. So if we look at a few examples of how some of these parameters can affect drinking water quality, we have pH again. So a low pH may increase the corrosion rate observed in a system. For alkalinity and dissolved inorganic carbonate, this can help control pH changes, and a low to moderate alkalinity tends to reduce corrosion from most materials. With total dissolved solids, if that reading is high, that tends to increase conductivity and also the corrosion rate. And then chloride and sulfide, if those high levels of those two parameters, that can increase the corrosion of iron, copper, and galvanized steel. Now, if we look at the general factors that govern lead levels in drinking water, you have the intrinsic lead solubility of the surface material, so how the various leaded components within a drinking water system are going to interact with the background water quality, so how much lead is going to dissolve because of the water chemistry. You have the water contact time with a lead source, so the longer a leaded source sits in contact with drinking water without moving, you're going to have more lead leach into the drinking water. But even if you have a short stagnation time, but you happen to have a galvanic connection where there are two dissimilar metals connected together, if one of them happens to be leaded, you can have higher lead levels observed in a shorter time frame because of that galvanic connection. There's also the nature of lead release, so you can have a particulate problem or a soluble problem. Some systems have both soluble and particulate lead, and if you're dealing with particulate lead, those tend to show higher lead concentrations in drinking water because you have actual little pieces of lead tin solder chipping off, or potentially pieces of lead service line scales, so that you're going to have really high lead concentrations. And now, while the sampling protocol doesn't necessarily govern the lead levels in the drinking water, it does govern the lead levels that you observe in the drinking water, because depending on the various variables that you take into account when you collect your sample and how you collect your sample, that's going to determine the lead concentrations that you observe and the subsequent results that you get back. And as a few additional points, unfortunately, there are no accurate substitutes or surrogates for directly monitoring lead release to drinking water. We can't look at a specific water quality parameter or a corrosion indice to tell us whether or not there is lead in the drinking water. The only way is to sample for lead at the tap and see what those concentrations are. And moving into the factors that control lead release from brass and soldered joints, you can have poorly made soldered joints, so where you have excess flux that cause the solder to run outside the joint and onto the interior pipe surface. So you've increased the surface area of the solder, and then that is more surface area that's available to the drinking water for the lead to dissolve into. And then galvanic interactions, like I mentioned on the previous slide. So when you have two dissimilar metals connected, depending on the water quality, one of those metals is likely going to be sacrificial to the other. And if that material that's being sacrificed happens to contain lead, such as a brass or potentially a lead service line, then you're going to have lead being released into the drinking water. Now, copper release is a little bit easier to predict. Copper is mainly controlled by pH, alkalinity, and the dissolved inorganic carbonate content, along with the oxidation reduction potential and the persistence of oxidants in the system, such as dissolved oxygen or any type of disinfectant that's used, like free chlorine. Orthophosphate is not really applicable necessarily to a private well system unless it's being fed. But one of the really interesting things about copper is that the copper scales in the inside of copper pipes age over time. So when new copper is installed, that's actually when you tend to get the highest copper levels observed in the drinking water, because over time the scales recrystallize to less soluble forms. And so the older the copper pipe is, the less copper is typically released over time. So these scales recrystallize over years to decades, and you get lower and lower copper release as the scales recrystallize. And then the stagnation time, this differs a little bit from lead. So if you collect a copper sample after a 6-hour stagnation, you're typically going to have a lower copper concentration than if you waited 16 hours. So copper dissolves a little bit slower into the drinking water than lead. But in pH and alkalinity controlled systems, if your pH is greater than 7.5, you typically don't have any problems so long as the dissolved inorganic carbonate is less than 35 milligrams per liter. And the same if the dissolved inorganic carbonate is less than 5, you typically don't have any problems so long as your pH is greater than 7. Now going back to overall water quality, it's really important to understand what your background water quality is because certain water qualities can cause excessive leaching or byproduct release. And so knowing these characteristics of your specific water will allow you to evaluate whether or not a particular material will be impacted. And it's also really good to know what other components might be in your drinking water, if there's potentially any other elements of concern that you might want to potentially filter out from your source water before it gets into your premise plumbing, or perhaps you want to use a point of use device in order to filter it out before somebody happens to drink it. So if present, certain metals like iron, manganese, and vanadium, along with radionuclides, can actually accumulate on pipe scales and then be re-released into the drinking water. And some of those elements do have health effects, so you don't necessarily want to be drinking them if they are present in high quantities within the source water. Now earlier I had mentioned the NSF 61 Drinking Water System Components Standard, and this standard looks at various plumbing components and how they leach contaminants of interest into the drinking water. And so it uses a set of standard waters to test these plumbing components in. But unfortunately, because of the range of water qualities that are in the United States, they don't have a standard water that is going to represent every type of drinking water that a product may come into contact with. And so in recognizing this, the NSF 61 standard created the informative Annex 6 within their standard. And what this annex does is it helps to provide some information on when a particular water chemistry conditions could cause leaching and byproduct release. And it has specific criteria for copper and galvanized steel materials. And I'm going to go over a little bit of the copper portion of Informative Annex 6. The galvanized steel portion requires a couple different water quality parameters and some equations to be performed before it can say whether or not a particular water might be aggressive to galvanized steel materials. But if we just look at high-risk waters for copper corrosion, within NSF 61 Informative Annex 6, assuming no orthophosphate is used, which is likely the case for most private water systems, waters at high risk for copper corrosion include waters where the pH is less than 6.5, so you have are more acidic conditions. If the pH is between 6.5 and 7 in a disinfectant or an oxidative treated water, and then you can see there's a couple of other scenarios here where the water would be considered to be at high risk for copper corrosion. Now moving into sampling, so if we want to identify the various sources of lead or copper in a premise plumbing system, there's a couple of different things that we need to keep in mind. And the first is that sample volumes represent source position in plumbing. And this is kind of the most important aspect to keep in mind when you're looking for various lead and copper sources in a premise plumbing or private well system. And so just to illustrate this, here we have a 1-liter bottle. And if we just focus on the copper type M pipe, we have 1/2-inch copper type M, and we have 3/4 inch copper type M. And so 1 liter is going to represent 9.8 feet of the 3/4 inch copper, and 1 liter will represent about 20 feet of the 1/2 inch copper. And so where this is particularly important is, say from the faucet that you're sampling at, you're interested in the lead release from a water meter that is about 15 feet away, following the plumbing map, from the faucet. If you happen to have 3/4 inch copper and you take a 1 liter sample, you're only making it 9.8 feet into that length of plumbing. So you're not going to be capturing any of the water that is sat stagnant there in your water meter, which was 15 feet away from the faucet that was being sampled. So it's really important to remember that the volume of water sitting within the various plumbing components is what it is that you're sampling in your sampling bottles. Also, unfortunately, lead and copper sources can be distributed throughout the plumbing. So this is an example of a premise plumbing system in a home, and you can see that there are various potential sources to lead and copper, various valves, fixtures, fittings, soldered joints, and they're kind of scattered throughout the entire home. This comes into play a little bit more in private water systems, because not only do you have the lead and copper sources distributed throughout the premise plumbing, but you also have lead and copper sources distributed throughout the wellhead area and pressure tank and various other plumbing components that are associated with that private well. So again, the volume of the sample matters, and faucet sampling can catch valves. So if we're particularly interested in whether or not a faucet is contributing lead to drinking water, it is a good practice to take smaller volume samples so that way you can isolate particular fixtures. So if you look at the faucet example on the left, if you happen to take a 250 milliliter sample from that faucet, you're going to encompass a lot of different valves and soldered joints along with the faucet itself. So if you happen to get a high lead level from this 250 milliliter sample, you're not really going to know which component actually contributed lead to the drinking water. Now, if you take a smaller volume sample, say 60 milliliters, that's really going to isolate the water that's sat stagnant within the faucet itself. And so if that sample comes back high, then you can say that most likely the faucet is the main problem, and you can replace the faucet and then test again and see whether or not that has removed the lead being added to the drinking water. So the main point here being that a lot of different plumbing fixtures and fittings can be included in larger volume samples, and that can really dilute the amount of lead that's measured in the samples that are collected, and it can muddle your sources. So you can't really figure out whether or not it's some soldered joints that are contributing lead to drinking water, or if it's really just the faucet itself. Now, in order to sample for lead sources and figure out where the lead is coming from, we like to use a technique called sequential sampling or profiling. And the first part of this particular type of sampling strategy is to map the interior plumbing and the approximate exterior route to the main, or in the case of a private well system, to the wellhead, in terms of the lengths, the internal diameters, and the visible materials. And you kind of have to guesstimate, because sometimes you can't necessarily see all the materials that are there. You then want to be able to flush the system completely and allow the water to sit motionless and stagnate for at least 30 minutes, but preferably at least 6 hours or more. And then you'll go back to the faucet that you map the plumbing from, and you'll take successive samples of variable volumes, whichever volume you desire, and however many samples it is that you need to get to the end point. And so what this allows you to do is to differentiate different plumbing components along that length of plumbing. And this is just an example of that. Here we have total lead by the sequential volume. For the faucet, 2 smaller volume samples. These were 250 milliliter samples that were collected to capture the faucet in this particular residence, and then the plumbing changed to PEX, to copper, and eventually to the lead service line. And so you can see that our lead levels do increase as we get into the lead service line. In addition to just looking at lead or copper in a sequential profile, it's sometimes useful to look at other metals. So in this case, we looked at iron and zinc. If you're dealing with galvanized plumbing, it might be useful to add in cadmium as well. So here we can see that we had in the 2 smaller volume samples, we had kind of an increase in zinc, so that zinc is coming from the faucet and then it kind of drops off. We can see that copper increases right where we had mapped the copper in the plumbing and then decreases again. And then iron kind of maintains the steady state and then increases as we get to the water main. So in this particular system, there was an iron water main that we were taking samples out to, and so this increase in iron shows that we were getting into that water main. But this using different metals can be helpful to figure out whether or not you map the plumbing appropriately. So if you weren't able to see a portion of the plumbing, you can see what signal, what metal is coming through in the water sampling to kind of confirm what it is you thought was there, perhaps behind a wall or someplace where you can't see. So it can be a nice confirmatory type sample. Another thing to keep in mind, though, with the profile sampling and sampling for sources is that with increased distance from the lead source, the total lead concentrations do decrease. So this is an example from our home plumbing system here in Cincinnati, and we have it in our lab. We have a lead service line installed, and then we have various faucets that are sampled from. And so this shows the sequential profile samples taken from 4 different faucets, and faucet number 4 is the closest to the lead service line. And you can see that that showed the highest total lead came from that faucet's sequential profile. And then as we get further and further away from the lead service line, the maximum lead observed in the profiles from the various faucets decreases. So this is particularly important to keep in mind in a private well system because there is a dilution effect. So if you have the distance between the well and the residence can be great, and that can cause the metal concentration captured in a sample to be reduced. So you might want to consider taking a profile from several different taps if available. So if your wellhead is pretty far away from the house, you might want to just take a sequential profile from the wellhead area if there's a sampling tap there. And then another sampling profile may be closer to the pressure tank, and then one from a faucet within the residence itself, just to make sure that you don't dilute any potential lead or copper sources from those different sections of the system that could be diluted due to the distance away from a single sampling tap. And finally, estimating exposure. So this is looking into whether or not somebody is being exposed to lead or copper in their drinking water. And there's a lot of different site-specific variables that contribute to exposure. I'm not going to go over those today, but it really deals in how the water is used, how long it's stagnant, where it moves within the plumbing itself, and any patterns that might change. But there's a couple different ways that we can go about sampling for lead in drinking water for exposure, and that's automatic versus manual composite sampling. So this collects lead under normal use conditions and captures a range of flow rates, stagnation times, flow durations, and temperatures. So this automatic composite sampling device, here you can see it's set up in a kitchen faucet. We have the tap that's used for water consumption, and then every time water is drawn for consumption, 5% of that flow is diverted into a sample collection bottle there on the right. So you can see this kind of takes up a lot of space, and it was deemed kind of inconvenient and cumbersome to residents. So instead, manual composite sampling might be something to look into, and so this is of all the water that's drawn for consumption, a small volume is poured into a collecting vessel, and you can create a composite sample over a day's use, a few days, a week, whatever time frame it is you want. You just adjust the composite sample collecting vessel volume accordingly. And so in this particular instance, after a period of time, the composite sample can be analyzed for lead or any other contaminant, and you can get an average lead concentration over whatever period of time it was collected. And finally, one takeaway on sampling is that wide mouth bottles are preferable to allow for a higher flow rate that's more typical of normal use. So you want to be able to sample drinking water at the flow rate that you would turn on your faucet to get a glass of water. And narrow mouth bottles, since you're trying to make sure that the stream stays within that narrow mouth, you're typically turning on the faucet at a lower flow rate. So you really want to have the wide mouth bottle so that way that's not an impediment. You can collect water under normal use conditions. So in summary, multiple water quality parameters can have an impact on metal corrosion in a system, and different plumbing configurations and water quality parameters can impact various sources of lead and copper differently. Lead and water can be highly variable, both spatially and temporally, and lead and copper sources can be distributed throughout the premise plumbing and also the well components. And when you're conducting a sampling event, the entire system needs to be considered, both the well and premise plumbing and all potential sources of lead and copper. And it's really important to identify the proper sampling protocol for the question at hand, whether or not you're identifying sources, estimating exposure, or you're looking into something else. So with that, I'll take any questions that you might have. Thank you.
Jennifer, thank you. That was you covered a lot of material. I'm impressed. The thing that struck me, and I wouldn't have thought of this if I didn't see it on your slide, is that most people consider pH the indicator of whether you're going to have corrosive or aggressive water. And clearly, you showed that, especially with alkalinity, pH can be as high as 7.5. and you can still have aggressive water. And I think that's an important consideration for everyone, if they didn't catch that, to understand. We do have a couple questions, and so we'll go right to those. We have a few minutes. So Walt Kelly asks, what's your opinion on the various corrosivity indices? The one that's used a lot isn't necessarily meant to be a corrosion indices. It's a scale forming indices, and I know that's a big issue.
Correct. Yeah. So the various indices are useful for their specific purpose. So like the Langular index deals in calcium carbonate precipitation. And so that's good to know. You don't want to have an oversaturation of calcium carbonate because then you'll have everything kind of scale up. But they are not directly relatable to lead corrosion or metal release. So they have to kind of keep those things separate when you're looking at the different indices.
Yeah, and I know there was a paper that came out about that use a Langular index, and it's frustrating when those things happen.
Indeed.
All right. Okay. Next question is, are those PB or lead sample volumes for various size pipes reflected in the EPA's school plumbing sampling protocols?
Yes, so that's a good eye because those figures are actually in the EPA's 3Ts sampling guidance. And I'm pretty sure it's in an appendix of the 3Ts document where it talks about because the 3Ts is kind of a standard across the board, and all of the examples is a 250 milliliter sample. But that's just a general guideline, and it does say to go through the appendice if you have different types of plumbing or faucets and you really want to drill down to what is the particular source of lead or copper to the drinking water, you've got to take smaller volume samples, and that's really site specific. So your faucet that you're sampling might not hold 125 milliliters or whatever that sample is. Maybe it's a smaller faucet and you need to take a 60 milliliter sample if you really think that sampling tap is what's causing your high lead concentrations.
Okay, last question. How does this apply to galvanized pipes?
So galvanized pipes contain lead in most cases. So that coating can release lead over time. And also if there happens to be any lead source upstream of a galvanized pipe, like a soldered lead tin soldered joint or a brass valve or fitting, when lead's released off of those components and it flows through a galvanized pipe, it can actually zorb on to that iron scale that's formed and then release itself. So over time, you've created another sink for lead, and that's another source of lead to drinking water. So galvanized pipes are a bit of a pain because they're just also another long-term source of lead unless you remove them.
Well, and that can be a source of particulate lead, especially, right?
Yes.
Yeah. And that's a harder animal.
That's a harder problem to solve in a lot of cases.
All right, well,
that's random.
Is another question. Hopefully you can get in the chat. There's a couple, but we need to move on. It's after 11. And so if you could deal with the chat, that'd be great. Thanks for your talk. It was very, it was hopefully a lot of folks, if you didn't catch everything, it's worth watching again. It'll be recorded. So there's a lot of good information in there about lead and copper and corrosion and the things we need to know to tell well owners. So thank you.
Yeah, you're welcome.
All right.